Hi, everybody. For the last lecture of the semester, we're going to be looking at one sample and two sample t-tests. All right, so um, generally speaking, we don't use the normal distribution when performing hypothesis tests, and that's what we've been using so far. But like I told you, we are kind of to start with making some assumptions that won't hold up in reality. In reality, we don't know the population standard deviation. But so far, we've been assuming, just kind of to set up the logic of what we're doing, we've been assuming that we know the population standard deviation. But when we're trying to figure out, stuff about what does the true population mean, we don't really know any of the population parameters. We don't know. We might know the population size, but we're not going to know the population mean. We're not going to know the population variance or standard deviation. And because we don't know the standard deviation, we have to estimate it using the sample standard deviation, so S. Um, so um, we need a slightly different method, a slightly different altered method than the one using the normal distribution because we're using S instead of the population parameter. And so we use the student t distribution, or t distribution for short, which we can use when we do not know the population standard deviation, and either the sample size is greater than 30 or the population has a normal distribution. So there are some limits on when we can use student t. You need either a population greater than approximately 30, and this this is more a number by convention. There'll be some level of argument as to what the real number is here, but for us, we'll just say 30, or that we can, assume with some confidence that the population itself is normally distributed. If the population itself we can estimate is normally distributed, then we can use student t with any sample size. So the t distribution is very similar in shape and symmetry to the normal distribution. In fact, when you take a look, if I just put up a student t distribution, many of you would just look at it and say, well, this just looks like the normal distribution. In appearance and in most of the features, so in terms of shape and symmetry, it looks quite a bit like the t distribution, but it's been slightly adjusted. And it's slightly adjusted to account for greater variability that's expected with small sample sizes. So when we're dealing with small sample sizes, we expect more variability in so with larger sample sizes, we think we're more confident that the mean and sample standard deviation will be close to the population mean and population standard deviation. With smaller sample sizes, we expect both of these kind of sample characteristics to potentially vary. There would be a lot more variability, right? So if you just take a tiny sample, there's a higher chance that both the sample mean and the sample standard deviation are quite different from the population one. So the student t distribution takes into account that there's differences in the variability that we would expect depending on sample size. So the real value of the t distribution that allows us to extend ideas of confidence intervals or hypothesis tests to many cases in which we cannot use a normal distribution because we do not know the population standard deviation, right? Because everything we've done so far, which has been really useful in terms of setting up how we can do hypothesis testing, has been on the assumption that we know the population standard deviation. Because in reality we don't, we'd kind of be dead in the water. It'd be nice. It would be nice theoretically that, hey, we could do this wonderful thing if we do the population standard deviation, but in practice it would be useful. So what the student t allows us to do is to extend it, actually find confidence intervals or conduct hypothesis tests, even when we're just relying on sample statistics. So if we just have a sample mean, sample size, and sample standard deviation. Now, do always bear in mind that it does not work in all cases. So if we have a small sample size of 30 or less, or the sample data suggests that the population has a distribution which is radically different from a normal distribution, then neither the t distribution nor the normal distribution applies. And such cases require other methods. So there are even cases, even with large sample sizes, where student T won't perform terribly well. We're not really going to cover that in this class, particularly in a condensed version. We're not really going to talk about it, but just do bear in mind that there are certain limitations, particularly related to sample size. But even when we've met the sample size requirements, there are certain cases where students T won't perform terribly well. And there's a whole slew of other methods that we can use, but we're not going to talk about them this semester. So here's a comparison between a couple of student T distributions and a normal distribution. So this is meant to be kind of your normal distribution, a couple of student T distributions, so representing, we can think of it as distribution of sample means in different cases. And so here we've got the standard normal distribution in blue. And in red, we've got student T distribution with n equals 12 and student T distribution with n equals 3 further down. And so while the shape is really, really similar, so symmetrical, kind of both of them have, all of them having a bell type shape, the smaller the sample size is, the heavier the tails get. So see, by heavier tails, I mean more of the percentage of results are expected to be found out in the tails. So the normal distribution has very low tails, right? Very quickly, it gets right near the axis, and there's very small percentages expected to be out here. The smaller the sample size we get, the heavier the tails become, and more is expected to be out here, and less is expected to be clustered around the mean. And like we already talked about, this takes into account the fact that with smaller sample sizes, we expect there to be greater variability in the means that we're going to find. With larger sample sizes, we expect all the different sample means to cluster more around the true population mean. But with smaller sample sizes, we expect greater variability. And so that greater variability is taken into account by the shape of student T, with more of the cases, say, out in the extreme and less in the middle regions. And so each different sample size will have a different student T distribution. You don't have to know how to draw them, just kind of understand the logic of it. So these are essentially normal distributions that have been slightly altered, particularly in terms of the distribution of how much is in the tails, to account for greater variability when we have smaller sample sizes. So versus normal distribution, so T distribution, so can be used when population standard deviation is not known and the population is normally distributed. This is usually based on assumption that the population is normally distributed because we don't know the population parameters itself. This is more just based on kind of assumption. Is it, reasonable to assume that, say, IQ scores are normally distributed in the population? And if we look at how, say, population IQ scores are constructed and what they're meant to represent, is it a reasonable assumption to say that population scores are normally distributed? Then we have, say, or IQ scores are normally distributed. Then population standard deviation is not known, and the sample size is greater than 30. So even if we don't think that the population is normally distributed, if we have greater than 30 in our sample size, we can still use the T distribution. And then we use a normal distribution pretty much in any case where the population standard deviation is known. So how do we construct confidence intervals using a T distribution? We've already seen how to construct confidence intervals when we're using the normal distribution, but now we're going to be using the T distribution, and so we need to find out how we can do that. To specify a confidence interval, we must first calculate the margin of error. So this, so far, it's the same as what we had before. But there's a slight difference when we're using the t-distribution, right? We don't know the population standard deviation, so we've replaced it with the sample standard deviation. And before we're multiplying by a constant, we've replaced that constant number with a variable. So here we've got n is the sample size, so this is like before. S is the sample standard deviation, so it replaces the population standard deviation. And t is a value that we look up in a table. And so before, when we were using the normal distribution, like I said, we had a constant here. Now we have a variable called t, and we find this from a table. So it's a little bit more complex than with the normal distribution, because you've got to look up this constant and you have to know how to find it. But we'll see in the coming slide that it's actually quite easy to find this constant. Okay, so to find this constant, we need to find the degrees of freedom for the sample data. We're not really going to get into what degrees of freedom mean in this class. It's a little bit beyond what we need. So I'm just going to tell you how to find it. And in later stats classes, you can learn what degrees of freedom kind of really mean. So to determine the degrees of freedom for the sample data, defined to be the sample size minus 1. So the degrees of freedom when we're doing finding the confidence interval is just V for degrees of freedom, just what we're using, is equal to n minus 1. You already know the sample size, you just subtract 1 and you know what the degrees of freedom are. And then table 10.1 on the next slide shows degrees of freedom in column 1. So you find the row corresponding to the number of degrees of freedom in your sample data, and then look across the row to find the appropriate t-value. So you just find the row with your degree of freedom, and then you take the value that's beside it. Now, it's a little bit complicated at first because there's multiple columns, but I can talk you through it. So we're pretty much always going to go with the 0.05 level. So here's your degrees of freedom. So say you've got a degree of freedom of, let's go with 16, because it's still on this side rather than going over to this side, right? So if you're doing a two-tailed test, right, you go to, and you want to be finding the 0.05 level, so the 95% confidence interval. You would look in column 2, and then go down and find, so for 16, we've got 2.120. If you're doing a one-tailed test, right, and we're looking at 0.05, so for 95%, we look at over here, and we use column 3, so 1.746. So you just have to know, are you doing a one-tailed test or are you doing a two-tailed test? And then find the appropriate value. So find your degree of freedom and then read the number from column 2 or from column 3, depending if you're doing one or two-tailed. And we call that the critical values. These are critical values. And these are just what we put in over here for T. So whatever number's there, use for T, then it's like you did before. So for confidence intervals with population means, the t-values correspond to 95% confidence intervals in column 2 and 90% confidence intervals in column 3. So when you're doing confidence intervals, we're always assuming two-tailed because it's going out both sides. So in that case, we'd always be using column 2. It's only if we're doing hypothesis testing with one-tailed where you go up here. But with confidence intervals, we're always over here. We're not really in this class working with 0.10. It's a standard that sometimes people use. But when we're doing confidence intervals, I'm pretty much always going to have you do 95%. So it will always be column 2 if we're doing confidence intervals. Once you find the t-value for your data and the confidence level, you can determine the confidence interval using the new formula for the margin of error E. And so you find the t-value from the table. The confidence interval, like I said, when we're doing it, it's always going to be 95. So it's always column 2. So you just take your degrees of freedom and read the number beside in column 2, and then plug it into your formula. And then if conditions require the use of the t-distribution, so population standard deviation is not known, and n is greater than 30, or the population is normally distributed, the confidence interval for the true value of the population mean extends from the sample mean minus the margin of error to the sample mean plus the margin of error. So this is the exact same as what we saw last time. This formula, so the confidence interval formula for the population mean is the exact same equation. It's the exact same as what we saw last time. The only difference is that E has a slightly different formula, with S replacing the so the sample standard deviation replacing the population standard deviation, and T, which we just found on the previous slide, replacing the constant that we had. And so once you found E, you just plug it in here and here, and you've got your confidence interval. So let's try an example. So here are 5 measures of diastolic blood pressure from randomly selected adult men. So we got 78, 54, 81, 68, 66. These 5 values result in these sample statistics. So n is equal to 5, sample mean is equal to 69.4, sample standard deviation is equal to 10.7. Using this sample, construct the 95% confidence interval estimate of the mean diastolic blood pressure level for the population of all adult men. So pause, get all the information you need from here. Then on the next slide, I've got your table 10.1. So I'll advance it. And when you're ready, you can take that, and you'll need that for finding your value of t. All right, so how does the solution work? So we don't know the population standard deviation, and we don't have a sample size of it. Greater than 30. It's reasonable to assume that blood pressure levels for adult men are normally distributed. So because we can reasonably assume that blood pressure levels for adult men are normally distributed, we use the t-distribution instead of the normal distribution. So we're okay to go with t in this, student t in this case. So first step is we need to find our degrees of freedom. So with a sample size of n is equal to 5, the degrees of freedom are v is equal to n minus 1. So we have 4 degrees of freedom. For 95% confidence, we use column 2 in table 10.1 to find that t is equal to 2.776. So let's just go back quickly. Here's 4 degrees of freedom. We look over here because we're doing 2 tails. Column 2, 2.776. So then we use table 10. We now use this value along with the given sample size, n equals 5, the sample standard deviation, 10.7, to calculate the margin of error. So it's equal to 2.7, sorry, it should have been 776, not 766, times 10.7 divided by root 5 is equal to 13.3. And then the confidence interval is the sample mean minus the margin of error to the sample mean plus the margin of error. So from 56.1 to 82.7. So it's really similar to what we were already doing last time. The only real difference is this is based on the sample instead, and we had to find this number. But finding this number is actually really not that hard. You just need to take the sample size minus 1 and then look up in the table what is the value for that, for the critical value when you have that many degrees of freedom. Once you've got that, once you've inserted this in, it's pretty much the same formula as what you'd have when we were doing it last time. So let's give it another try. A simple random sample of men is obtained, and the elbow to fingertip length of each man is measured. The population of those lengths has a distribution that is normal. So we've got a normally distributed population. The sample statistics are n is equal to 35, sample mean is equal to 14.5 inches, and the sample standard deviation is equal to 0.7 inches. Determine the critical value of t and the margin of error, and then construct the 95% confidence interval estimate of the population mean. So get all of this down, and then I'll pause it as you get all of this down. Then I'm going to advance to the critical t value table. You can get your critical value of t from there. And then once you're ready and you found the answers, we can advance to the solution. All right, so the population standard deviation is not known, but we've already said it's reasonable to assume that blood pressure levels of men are, sorry, this shouldn't be blood pressure levels, but we've already said the elbow to fingertip levels are normally distributed. So we use the t distribution instead of the normal distribution. So it had already said in the instructions that it's normally distributed to the population. So with a sample size of n equals to 35, the degrees of freedom are v is equal to n minus 1. So 35 minus 1 is equal to 34. So we take this 34, and because we're doing a 95% confidence interval, we go to column 2. So 34, column 2, what do we get? 34, column 2, 2.032, right over here. 34, 2.032. And so we use column 2, and the critical value of t is 2.032. We now use this value along with the given sample size, n equal to 35, and sample standard deviation, s is equal to 0.7 to calculate the margin of error. So we've got 0.7, root 35, 2.032. And then so we end up with the margin of error of 0.2. Take the sample mean minus 0.2. Take the sample mean plus 0.2. And so we have a range, a 95% confidence interval of 14.3 to 14.7. All right, so that's showing you how to construct confidence intervals. How do we do hypothesis tests? So with the t-distribution, instead of calculating the standard score, we use the following formula to calculate t. Right. So remember when we were trying to do hypothesis testing, we had to find the standard score from our sample. Right. So if we assume that we had one sample mean, or we had one sample mean, and it was one example of a sample within the distribution of sample means. Before we were calculating what is the z-score, right? If we think of it as a standard normal distribution, we'd find what the z-score is for that particular sample, and then we can use the z-score table or the standard score table to find what's the probability of getting a sample at least this large. But now we're not using a normal distribution anymore, so the standard normal doesn't work or the standard score doesn't work. So we need the equivalent for the t-distribution. So rather than calculating the z-score, we now calculate, or the z-score, we now calculate the t-score. And if you take a look, really the format is the same, right? So we have our sample mean, we have kind of the hypothesized population mean, right? So kind of your null hypothesis type 1. We replace the population standard deviation with the sample 1 and over root n. So n is the sample size, x bar is the sample mean, S is the sample standard deviation, and U is the population mean claimed by the null hypothesis. So really this looks a lot like your T distribution, or sorry, your Z score calculator, but instead of, because we're no longer using the normal distribution, we're using the T distribution, we make changes based on our new information. In particular, the biggest new bit of information is that rather than having the population standard deviation, we have the sample standard deviation. So once we've calculated T, we decide whether to reject or not reject the null hypothesis by comparing our value of T to the critical values of T found in table 10.1. So the critical values depend on the type of test as follows. So if you're doing a right-tailed test, reject the null hypothesis if the computed test statistic T is greater than or equal to the value of T found in the column 10.1 labeled area in one tail. For a left-tailed test, we reject the null hypothesis if the computed test statistic T is less than or equal to the negative of the value of T found in the column of table 10.1 labeled area in one tail. And we'll take a look at this in a second. But essentially in either of these cases, right, we would reject the null hypothesis if our calculated test statistic T is more extreme in either of these cases, is more extreme than the critical value of T for our chosen confidence level. And so if you think about it like how we did before, we said, okay, so we've got our normal distribution, right? And our critical value was telling us that, you know, there's only, let's say 95% or 95% is in this part, 5% is in this part. We've got our critical value that's got our separating between this 95 and this 5, right? And we said before that if, so in our left-tailed test, if the Z score was more extreme, if our calculated Z score was more extreme than that critical value, so we're in that 5%, then we could reject the null hypothesis. It's the same thing here, but rather than using Z scores, we're using T scores. So in a right-tailed test, it would be, because we're looking out on this side, we would be seeing, is it greater than the critical value? Here, because the left-tailed, we'd be seeing, is it less than the negative of the critical value? Because the critical values in table 10.1, we just go back to table 10.1, are all written as positive. So if we're dealing with left-tailed, we just have to put a negative sign in front of them. And we're looking at area in one tail. So for 0.05, we're looking at column 2. And then two-tailed test, reject the null hypothesis if the absolute value of the computed test statistic T is greater than or equal to the value of T found in the column of table 10.1 labeled area in two tails. You take the absolute value of whatever you calculate, and you see, looking in column 2, is it more extreme than the critical value? And we're going to do examples to make this a little bit more clear in case it's not. And the calculated test statistic can also be used to find a p-value. However, that's usually done with the aid of a statistical software rather than with tables. So that's something that we may do in the final lab, but it's not something that I'm going to make you actually calculate. All right, so let's try an example, and hopefully this will make it a little bit more clear. So listed below are 10 randomly selected IQ scores of statistics students. So here they are. The data has the following sample statistics. Sample size is 10. Sample mean is 109.5. Sample standard deviation is 5.2. Using a 0.5 significant level, test the claim that statistics students have a mean IQ score greater than 100, which is the mean IQ score of the general population. So this is, IQ scores are meant to have a mean IQ of 100. That's what they're constructed to have, where kind of the average person would get an IQ score of 100. So we want to test the claim that statistics students have a mean IQ greater than 100. So if you get into the statistics class, you've got a mean IQ greater than 100. So that's what we want to be testing. So give it a try using the different steps. Remembering that really it's essentially the same as what we were doing last class, just with a few little changes related to the t distribution. And I'll put up the critical values of t. So once you've got all the information you think you need, I'll put up the critical values of t table. All right, so first we've got to start, like we did last time, by setting up our different hypotheses, right? We've got the null hypothesis is that the population mean, or the mean is equal to 100 for kind of statistic students. And the alternative hypothesis is that for statistic students, population parameter is greater than 100. Since the population standard deviation is not known, and IQ scores can reasonably be assumed to be normally distributed, we use the t distribution. So we're okay to use the t distribution. So whereas normally when we're working with the normal distribution last time, we start by finding the said statistic. Here we start by finding our t-tested statistic, right? And so that's our sample mean minus the kind of null hypothesis, the mean population mean from the null hypothesis, divided by the sample standard deviation divided by the root of the sample size. And so we end up with 5.777. We have, we need to find our degrees of freedom to know where to look in the table. And we find that v is equal to 10 minus 1, so is equal to 9, right? So now we want to see, because this is the right tail test, we want to see is 5.777 greater than the critical value that we'd find when there's a degree of freedom is equal to 9. So because it's a one-tail test and we're asked to test for significance at the 0.05 level, we use the values from column 3. Looking in the row for 9 degrees of freedom in column 3, we found that the critical value for significance at the 0.05 level is 1.833. So see if we look over here, 9, we're doing one-tailed, and we want 0.05, so column 3, 1.833. Because the sample test statistic t is equal to 5.777, it's greater than the critical value 1.833, we reject the null hypothesis. We conclude that there's sufficient evidence to support the claim that the mean IQ score is greater than 100. So it's very similar to before, right? We still before had critical values for the for standard score. The difference was because we only had one standard normal as opposed to multiple t distributions, it was a fixed constant, where here we've got to find what our critical value is, and we still compare what we get. So our calculated said t statistic, or before we calculated z statistic, and we compared it to the critical value. So we still compare a test statistic to a critical value, which is what we were doing before. The only difference is that we calculate slightly different. We use a slightly different formula to calculate our test statistic t, right? Because we don't have the population standard deviation, and rather than using a constant, we have to find our critical value using our degrees of freedom. So here's another example. The US Mint has a specification requiring that pennies have a mean weight of 2.5 grams. 30 randomly selected pennies have a mean weight of 2.49910 grams and a standard deviation of 0.01648 grams. The mean weight of all pennies is assumed to be normally distributed. Use a 0.05 significance level to test the claim that this sample is from a population with a mean weight equal to 2.5 grams. Do pennies appear to conform to specifications of the US Mint? So here's the critical values table for when you're ready. All right, so our null hypothesis is that the weight of pennies is 2.5 grams. The alternative hypothesis is that it's not equal to 2.5 grams, right? Because we've got our sample one, and we want to see, based on this sample, can we conclude that the weight of pennies is not equal to 2.5 grams? And this is a two-tailed test because we haven't said that we expect it to be larger or less. We just are testing whether it's different. Since population standard deviation is not known, and sorry, this should be IQ scores, this should be weights, penny weights, can reasonably be assumed to be normally distributed, we use the t distribution. So the t statistic is 2.49910 minus 2.5. So our sample mean minus the null hypothesis population mean. Our here we've got our sample standard deviation divided by our sample size, root of our sample size. And we end up with negative 0.119. Next, so this is our test statistic. But what we need is to find what do we need to compare this to, and see, is it more extreme than that? So to be able to know what our critical value is, first we need to find our degree of freedom. So degrees of freedom, we've got 30 minus 1, sample size minus 1, equal to 29. Because this is a two-tailed test, and we're asked to test for significance at the 0.05 level, we use column 2, because when it's two-tailed and we're going at 0.05, we always use column 2. Looking for the row for 29 degrees of freedom in column 2, we find that the critical values for this for significance at the 0.05 level is t is equal to minus 2.045. Let's go. 29, 2.045. So why did I write negative? Actually, there shouldn't have been a negative there. It should have just been 2.045. The reason I put the negative is because our calculated one was negative. So I could have taken the absolute value of this and compared it to the positive one, but with a two-tailed, you can also, if you get a negative one, put the negative of this. I went with this particular route based on the instructions I gave. I probably should have just taken the absolute value of this and compared it to the 2.045. Either will work. It's the same idea. You just want to see whether this is more extreme, or the absolute value of this is more extreme than this. And you could do it either of those two ways. Because the sample test statistic t is less extreme than the critical value, we cannot reject the null hypothesis. We conclude that there's not sufficient evidence to support the claim that the population has a mean weight different from 2.5 grams. Pennies appear to conform to the specifications of the US Mint. All right, so so far we've used students T when we've been doing hypothesis testing to test the null hypothesis that the population mean is equal to some claimed value. So in that last case, we said that pennies are 2.5 grams. Before we said that the IQ score is 100. So we had some claimed value. But oftentimes we're not comparing to some claimed value. We're comparing to another sample. And so here, what we've already been doing is what's called the one sample t-test. We've got one sample and we're comparing it to some claimed value. 2.5 grams per penny, which is the specification that it's supposed to be. 100 is the kind of population IQ. And so that's one sample because we've only got one sample. But we're now going to examine the use of students' t-test to test the null hypothesis that the population mean for two groups are equal. In other words, we test the claim that the population mean from sample 1 is equal to population mean from sample 2. This is called a two-sample t-test. So kind of an example of where we might be using this is think of a drug trial where some people get a sugar pill, and some people get some new medication. And so we look at, okay, how did people who got the sugar pill or the placebo respond? And then we look at how did the people or the sample that got the treatment respond? And what we're trying to do, and so we'll have say the responses, how quickly they recover from a sort of sickness. And say the people got sugar pills recover in 7 days, and people who got the treatment recover in 4 days, right? And so there's a difference between those two samples. What we want to figure out is, that's really it's fine for those samples, but we want to be drawing conclusions about the wider population. So we want to be seeing, is for the wider population, will people who get sugar pill or nothing recover more slowly than people who get the treatment, the population. So we want to scale both of those samples up the population and then compare. And so the alternative hypothesis will be that there's some difference between those two populations. So people who get the sugar pill will respond differently, either shorter, smaller, larger, or just not equal to those who get the treatment. And so because the null hypotheses are always equality, the null hypothesis is that the two population means are equal. So in this case, it'd be the treatment doesn't work, right? People who get the sugar pill in population, if they get the sugar pill, the mean response time will be the same as people who get the treatment. So the null hypothesis is to say the treatment doesn't work. So if we gave everybody the sugar pill, we gave everybody the treatment, the response times or the recovery times would be equal in both cases. And so this is referred to as a two-sample t-test, because we've got two different samples, right? Say we want to see, is there a difference between, for taking a test, whether you take it at 8 a.m. or noon. So we have one sample take, they went through the exact same class, exact same lecture, same teacher, same slides, everything, same office hours, but they had their class at 8. And then we've got another sample, same teacher, everything. They had their class at noon, they take the same exam, and we get their scores for, the 8 a.m. sample and the noon sample. But, that's interesting again for those two samples, but what we really want to be finding out about is the population. From those tests, can we say that people who take tests at 8 a.m. do, say, worse than people who take tests at noon? The null hypothesis will be that there's no difference, right? That if everybody took the test at 8 a.m. and everybody took the test at noon, their scores would be the same. So the following assumptions are made in a two-sample t-test. So we assume that we've random sampling, right? So the people who get assigned to your sugar pill or your treatment, it's randomly sampled who gets which one. The observations in group 1 are independent of the observations in group 2. So the people in, for example, in the 8 a.m. test can't have told the questions to the people in the noon test. Because then, the ones in the noon test would have an advantage. There can't be any sharing of drugs between, the people in the drug trial. If they know that some of them have a sugar pill and some of them have drugs, they can't say, hey, let's make sure we get some treatment. So every second day they swap pills. So they're guaranteed that every second day they'll get a sugar pill, but every second day they'll get a treatment, right? In that case, we're not going to be seeing any the true effects of the drug, right? Because everyone's getting the same. We're not getting a treatment in a control group. We're just everybody's getting the exact same thing. So you need the two groups to be independent. For both groups, sampling is from a normal distribution. So the overall population, you have to believe that the population is sampling from a normal distribution. And the two groups have equal variance. This assumption is called homoscedasticity. It's something that in reality gets violated a lot. We're not going to talk too much about it. We're just going to assume it to kind of be the case. But this can actually cause pretty serious problems. But the two groups are supposed to have equal variance. So the two populations should come. So essentially, populate, so the samples may look different, but we need to be assuming that the variance, say you've got noon and 8 a.m. tests, right? And we may assume that they've got different means, but we should assume that the variance in both groups is the same, right? So it may be that, the curves are shifted over, but the shape of both curves we need to assume is the same. So it can't be that, people who take it at 8 a.m. have a really wide curve and people who take it at noon have a really thin curve or distribution. That wouldn't work with a two sample t-test. So we need to assume, and this has to be done by assumption because it's not something that we're going to know, but we need to assume that both populations have equal variance. So first step is we need to find a common variance. And I know this formula looks scary, but on any test where we have it, I would give it to you. Usually the way I do is I don't give you this part, but you're going to have this entire thing. So all you're going to have to remember is that this equals common variance. And you're going to see in an instance why we need the common variance. But remember that generally speaking, the sample standard deviation is included in many of the formulas that we've been using. But what the common variance does is it takes the weighted average of the two sample variances. Because so in our calculations, say for confidence intervals or for hypothesis testing, we've included the sample variance. But if we've got two different samples, which variance do we use? And so which sample variance do we use? And the answer ends up being we use what's called the common variance, which is the weighted average. And so all you really need to know for doing it is actually quite simple, right? So you just need the sample size of sample one, the variance of sample one, the sample size of sample two, the variance of sample two. And I'll always be giving you the sample sizes. I'll always be giving you either the variance or the standard deviation. Be careful if I'm giving you the standard deviation. The variance is just the squared of the standard deviation. So if I give you the standard deviation, just be careful, you've got to square it. And then again, I'm giving you sample size one, I'm giving you sample size two. So with a calculator, this is actually really easy to do. And so you end up with the common variance. We want a confidence interval for the difference in the population means, right? So that's what our confidence interval is here. So normally what we're doing is when we're doing our confidence interval, we are doing it for what is the kind of the population mean based on our sample statistic. But here what we want to be doing is seeing is there a difference between these two groups? So we want a confidence interval for the difference in population means. So if our confidence interval doesn't include 0, then we can believe that there's a difference between these two groups. If the confidence interval crosses 0, then we don't believe that there's a difference. So how do we calculate this? So taking the critical value of t from a t distribution with, so again, we're still using the table 10.1, but we calculate the degree of freedom slightly differently. And again, I'll give you this formula on a test. So you're never going to have to remember that n plus 1 plus n plus 2 minus 2. All you're going to have to do is recognize it. Degrees of freedom for a chosen level of statistical significance, and we're always going to use 0.05. So remember, if we're always using 0.05, we're always using column 2. But to find where to look in column 2, you just use this V. So for a chosen level of statistical significance, so always 0.05. Confidence interval can be calculated by sample mean 1 minus sample mean 2. So that's essentially because we're trying to find, so that's showing the difference between the two means, plus or minus, which is essentially what we were doing before with our, when we were doing, sorry for going backwards. When we were doing this, we were essentially doing mean plus or minus, sample mean plus or minus margin of error, right? Because we're doing minus and plus. So essentially we were doing plus or minus, we're just writing it differently. So we could have been using that type of notation there too, but just to show that we're doing something very similar. So we're taking the difference in the sample means plus or minus t, so our critical value, or sorry, our critical value, our common variance, square root of our common variance, sample size 1, sample size 2. So you just fill those in. So common variance we've calculated over here. You know your sample sizes. So you put them in here and you get your critical value of t from column 2 using these degrees of freedom here. And we'll come back to an example here, but essentially, so if we find, say, the drug, so I said that one took 7 days and one took 4 days to recover, right? So we'd have, say, 7 minus 4. So there's a 3-day difference between these two sample means. And so what this would be telling us is our margin of error. So say we end up with plus 1. Say all of this adds up to 1. We'd say, okay, so we've got 3 plus 1, so 4 and 2. So we'd say that we're pretty sure that we're 95% sure that the difference between the population means is between 2 and 4. If a difference between the population means is between 2 and 4, then we're pretty confident that it's not 0, that the two populations aren't equal, right? Because the null hypothesis was that they are equal, so that there's no effect of the drug. So if we end up with saying that we're 95% sure that the difference between these is 2 and 4, then we can reject the idea that it's, or we kind of reject the null hypothesis that they're equal. So we're 95% sure that they're not equal. We're actually even more than that because it goes from 2 to 4. So to hit 0 would be even further. Where imagine all of this added up, so all of this added up to 4. So we would take a difference of 3 plus 4 is equal to 7. Minus 4 is equal to minus 1. So we'd be 95% sure that the difference between the population means is from minus 1 to 7. In this case, right, we can't be confident. We can't reject the null hypothesis. We don't have sufficient evidence because we don't know. We can't be 95% sure that they're not. These two groups aren't the same because we go from minus 1, we cross 0, right? So included in our range of possibilities is what the null hypothesis says. The null hypothesis says that the two are the same, that the difference between them is 0. Our kind of the range that we found admits that it might be 0. And we'll get into that when we talk hypothesis testing, but just to kind of explain what this would mean. So we're just finding kind of the range of possible values for, or at least that can be 95% confidence in for the difference between the two groups. So hypothesis testing more formally. So similar to a one sample t-test, we must calculate a t-statistic. So similar to the standard scores, we calculate a t-statistic that we compare to a critical value. So how do we, for when we're comparing two groups, so remember before we were doing sample 1 minus the claimed value. Here we're doing sample 1 minus sample 2. And then before we were dividing by, we had this, the root of the sample size, and we had the sample standard deviation. So here we've got the root of the common sample variance times this. And so that gives us our test statistic. And then we need to see, is this more extreme than our critical value? So we choose whether to reject or not reject the null hypothesis by comparing the calculated t statistic to our chosen significance level critical value of a student t distribution with v is equal to sample size 1 plus sample size 2 minus 2 degrees of freedom. We reject the null hypothesis if the absolute value of our calculated statistic, if the absolute value is greater than or equal to the critical value of t, which we find in table 10.1. And remember, we go into, if we're doing a two-tailed test, we go into column 2. If we're doing a one-tailed test, we go into column 3. So here's an example, which I think will show, this looked scary, but I think when you start plugging in the numbers, going step by step by step, you're going to see it's not very scary. And it's really similar to what we've already been doing. And I'm going to be giving you on the test, I'm giving you all the formulas. Like I said, the only thing I'm not going to give you is I'm not going to say that this is equal to t. You're going to have to remember, you're going to have to be able to recognize this and know this means for comparing the t for comparing two groups. So you won't get this, but you'll get all of this. You'll have essentially a sheet with this and all the other formulas, not what they're equal to, but all you're going to have to do is recognize them. So if you can recognize this and remember, okay, this is for two sample, and then you know how to use it, you're good to go. So here's an example. So Salk in 1973 conducted a study where the general goal was to examine the soothing effects of a mother's heartbeat on her newborn infant. Infants were placed in a nursery immediately after birth, and they remained there for 4 days except when being fed by their mothers. The infants were divided into two groups. One group was continuously exposed to the sound of an adult's heartbeat. The other group was not. Salk measured, among other things, the weight change of the babies from birth to the 4th day. For group 1, the sample size was 20, the sample mean was 18.0 grams, and the sample standard deviation was 60.1 grams. For sample 2, the sample size was 36, the mean was negative 52.1 grams, and the sample standard deviation was 88.4 grams. So A, what is the 95% confidence interval for the difference in the population means? So don't forget, so how do we have a negative here when we're talking weight? Don't forget it's weight change. So these ones got smaller, the other ones got bigger. So construct what is the 95% confidence interval for the difference in the population means, and can we reject the null hypothesis of equal means? And I'm going to put up the table 10.1. So pause it, get all the information, get all your formulas set up, and once you're ready for the critical value table, click play, and I'm going to post it. All right, so let's start by getting our common variance. So we get our common variance, again, using this formula. So we put in the sample sizes and the standard deviations, but we don't forget we need to square them because standard deviations, we're talking variance. But that's easy. You just plug in the standard deviation and square it. And the notation here even makes it easy, right? Because it's s squared. So if you've got s squared, just plug it in here. If you've got s, just put it in here, but keep the squared. And so all of this, and then the two sample sizes. And so this adds up to this value. For confidence interval, we start, don't forget, we need to find our degrees of freedom. So we've got 54. For 95% confidence interval, the critical value of t with 54 degrees of freedom is 2.01. And so we get that from column 2. And then we find the confidence interval. So we do sample mean 1 minus sample mean 2 plus or minus, so or plus and minus in this case, t times this, right? So we've got sample mean 1 minus sample mean 2 plus and minus 2.01 times all this stuff. And so we end up with 25.5 to 114.7. So we believe that the difference between them is anywhere between, so we're 95% sure that the difference between the two is from 25.5 to 114.4 between the two population means. So here's our hypothesis test for doing, our confidence interval for doing our hypothesis test. So we put in our T formula. So for getting our test statistic, so we 18 minus 52.1 divided by square root of our common variance with our two sample sizes, and we end up with 3.2. Then we still have 54 degrees of freedom. And then for 95% confidence with the two-tailed test, the critical value of T with 54 degrees of freedom is 2.01. Since the absolute value of this is greater than 2.01, we reject the null hypothesis of equal means. So we can conclude that, we have evidence for the conclusion that something happened. And I'm going to be putting up exercises for all this so that you can try getting some practice with doing your one sample and two sample t-tests. That's the end of our last lecture. So have a really good day.